Chapter 5, Applying Forces. Let's learn physics force, physics force. I want to learn physics forces. All right, I tried. All right, so chapter 5 is a heck of a lot harder than chapter 4. Woo! Hang on to your chairs, because here we go. Okay, so we've already learned about force diagrams and how you can put together a force diagram. Now, let's assume that forces are in equilibrium. So in order for forces to be in equilibrium, that means that acceleration is equal to 0. Because the net force, the total overall forces, have to add up to 0. So the net force equals to 0, the sum of all forces is equal to 0, and if there's no net force, then there's no net acceleration. So that could happen if an object is at rest or if it's at constant motion, because remember, any constant velocity means no change in velocity, so that means no acceleration. You can also look at equilibrium and break it down into its x and its y components. So I could say all of the sum of the x forces are equal to 0. So that means the mass times the x acceleration equals 0. And the sum of the y forces has to be equal to 0. So the mass times the sum of the y accelerations equals 0. So let's do this little sample from the textbook. Figure 5.2 kind of sets it up for us, and they've done the little diagrams. So I'm going to take it from there. The textbook goes about it in a very confusing way. They use lots of equations to try to add things up, but I'm going to do it more visually because I think it makes a little bit more sense. So the first part is I'm solving for the tension on a horizontal wire. So here's my horizontal wire holding my wrecking ball. And then I also have a vertical wire that's at, well, it's not totally vertical. It's at a 20-degree angle off of vertical. And each of those wires is going to have tension on them. I want the tension on the horizontal wire. And I also know that there's a weight of the wrecking ball that is 2,500 newtons. Okay, so when I draw my force diagram, I see that I have the weight going down. That's a vertical force. And then I also have the tension going up. The horizontal wire over this way has no weight on it because it's horizontal. It's not vertical. So the vertical component of the weight has to be up here, right? So the purple going up has to match the purple going down. So the vertical component of tension on that has to match the vertical component, and then the horizontal component of tension that way has to match this green horizontal because I know that the ball is at rest, it's not moving. So because I just need the tension on this wire, I need tension number 1, I can ignore these purple ones. The purples are going to cancel each other out anyway, right? So I just need to find this green arrow, which is the same as this green arrow. So if I want to figure out the total value there, I just need the horizontal component of this wire, and I know that the vertical component is going to be equal to the 2,500 newtons. So over here, I could put in, here's my 2,500 newtons. I know that that angle right here is 20 degrees, which means that this angle is also 20 degrees. So in order to find that component of it, I could do some trigonometry, and I could say, let's see, I need that part. That is the opposite to the angle, and I have the adjacent. So that would tell me the tangent of theta is equal to opposite over adjacent. So the tangent of 20 is equal to the opposite, x, over the adjacent, 2,500 newtons. X equals 2,500 tangent of 20. Now all I have to do is plug that into my calculator. On 2,500 tangent of 20 gives me an error because I forgot to multiply, 2500 times the tangent of 20 gives me, I keep making mistakes, 2500 times tangent 20 equals 909.9 or 910 newtons. So X equals 910 newtons. Nice. So I broke it down into the horizontal and the vertical components, and that made a tremendous amount of difference. Much easier that way. Okay. What else? And this was a reminder that I should solve for the Y component and then the X component. So the Y component was 2500. The X component was 910 newtons, right? Based off of the tangent. All right, let's do a little stop and think. A ball of weight 200 newtons is suspended from two cables, one horizontal and one at a 60-degree angle, as shown. Which of the following must be true of the tension in the angled cable? Okay, so I know that this is 200 newtons, and I'm trying to figure out the tension. Well, I know that the vertical component is 200 newtons, so then the vertical component going up has to be 200 newtons, but then it's also going to have some horizontal component on it, right? Because I need that horizontal component of tension. So 200 plus the horizontal component will have to be more than my 200 total. So I'm going to go with more than 200, which would be part A, right? Because it got the vertical and the horizontal. Okay. For dynamics, dynamics are when we have things that are not in equilibrium. God, so now there's going to be movement as well as vertical and horizontals. Trigonometry plus some movement. So just a reminder that I can use, now I'm not going to set it equal to 0, but the sum of my x forces will be mass times the acceleration in the x direction. The sum of my y forces is going to be the mass times the acceleration in my y direction. So let's do this example, putting a golf ball. A golfer puts a 46-gram ball with a speed of 3 meters per second. So I've got 3 meters per second, and that's a velocity in the x direction. I've got a mass there. Friction exerts a 0.020 Newton retarding force on the ball, slowing it down. Okay, so that's the force of kinetic friction right there. Will her putt reach the hole 10 meters away? So 10 meters away, that's an change of x. All right. So I'm going to start by drawing my force diagram because this one seems to have some stuff going on. I know that I have a weight force, W, and that's going to be balanced out evenly. Sorry, this should be vertical, by a normal force because it's on a putting green, so that's a flat surface, and it's not going into the ground, so those should balance. When it's rolling, the only other force on it is that force of kinetic friction pushing it, slowing down. So I've got a force of kinetic friction, and I happen to have a value for that one, 0.020 newtons. Okay. And this weight is due to the mass. So I also know, given there is a mass, which is equal to 46 grams, which is equal to 0.046 kilograms divided by 1,000. Okay. So will her putt reach the hole 10 meters away? Well, the first thing is that I can kind of ignore these ones because they're going to cancel each other out. So all I've got, my total net force, is the force of kinetic friction, 0.02 newtons. So I could start by finding its acceleration. Force of x equals mass times acceleration in the x direction. I can ignore the y's because it's not moving in the y direction, up and down. Then I can solve for acceleration. Acceleration is equal to force over mass. So my acceleration of the golf ball is going to equal the force 0.020 newtons over the mass 0.046 kilograms, giving me an acceleration of 0.02 divided by 0.046, 0.435. 0.435 meters per second squared. And I know that's going to be a negative value because it's slowing down. So I should be reducing in speed. Okay. All right. Now, I really, in this problem, new sets of needs. Now I need to know how far the ball goes. So I need the change of x. I know that it has to go at least 10 meters, so I'm going to compare it to 10 meters at the end. I am now given an acceleration of negative 0.435 meters per second squared, and I'm given a speed, an initial speed, v sub 0 in the x direction, or v sub x0, I think I put them the wrong way, of 3.0 meters per second. And I know eventually it's going to come to a stop, right? I want to make sure that it goes in the hole and gets past 10 meters before it comes to that stop. So my final speed will be 0. All right. Now I've got this distance, acceleration, velocity, velocity. Aha, that's one of my kinematic equations. I remember those. So let's plug that in. That would be the v squared, v sub x squared, equals v sub x0 squared plus 2a change of x. I can plug everything in except the x. My v sub x is 0 squared equals 3.0 meters per second squared plus 2 times negative 0.435 meters per second squared, yeah, times delta x. That becomes negative 9 equals 2 times 0.435, 0.87, negative 0.87, and then delta x equals 9 divided by 0.87 gives me 10.3 meters. All right, so the ball will travel 10.3 meters before stopping. The hole is 10 meters away. So yes, as long as I hit it, or as long as she hits it in a straight line, 10.3 meters is more than 10 meters, so it will get there. Yes, hooray, a hole in one, or I guess if she's on the putting green, it's probably not a hole in one unless she's playing mini golf. All right, let's do another example. Another fun one with dynamics. Okay, a car with a mass of 1,500 kilograms is being towed by a rope held at a 20-degree angle to the horizontal. A friction force of 320 opposes the car's motion. What's the tension in the rope? So I need, that's what I'm solving for, the force of tension, if the car goes from rest to 12 meters per second in 10 seconds. Okay, so again, I'm going to draw my force diagram here. I have a weight of the car. I have a normal force because the car is sitting on the ground. I have a friction force pushing back this way of, so that's a force of kinetic friction of 320 newtons. And then I have a tension force on this rope, and I think that's going to be a pretty big one because it's pulling the car forward, so it's overcoming that friction force. That is a 20-degree angle, and that is the force of the tension. and I'm trying to solve for that guy. Okay. So the first component is trying to figure out, I know that I'm going to end up with some acceleration in this direction, right? I have to end up with some, so my overall force net has to be that way, which means my acceleration has to be in that direction. So let's start by figuring out the component to the right, because I think I can find my acceleration, right? The car goes from rest to 12 meters per second in 10 seconds. So if I find the acceleration, then I could do the mass times the acceleration and figure out the horizontal component of force. And I think I can go from there. Okay, so I know that acceleration is the change of velocity over the change of time. And I go from rest to 12 meters per second. So that's a change of 12 meters per second in 10 seconds. 12 divided by 10, 1.2 meters per second squared. So now I have an acceleration to the right from that. Now I could do an F equals ma, and this is the force horizontal, right? So that's the force X of the tension rope, is going to be equal to my 1,500, because the mass is the what's moving, right? 1,500 kilograms times 1.2 meters per second squared. 1.2 times 1,500 gives me 1,800 newtons. Okay, so overall, I need a net result of 1,800 to the right. But I also have to overcome that 320 force of friction, right? So then the tension on the rope has to be my 1,800 plus my 320 newtons to overcome that force of kinetic friction, right? Because my force net has to equal 1,800. And so I have to get 18 plus 3 would be plus 320, 2120. So 2120 newtons would be the horizontal component over here on my force diagram, right? So here I got to get that to be 2120 newtons, right? In order to get the horizontal component of the tension. Now I have the horizontal component. Oops, lights went out on me. There we go. I have the angle and I need the total value. So I can do a little bit of trigonometry again. I have the adjacent and the angle. Cosine is adjacent over hypotenuse. So now I'll do cosine of 20 equals adjacent 2120 over t. Multiply both sides by t, divide both sides by cosine. T equals 2120 newtons over cosine of 20. So I'm going to divide that by cosine of 20, giving me 2,256. So let's make that 2,000. Let's see, how many digits do I have to play with? Basically 2 digits of accuracy. 2,300. So that's 2,256 newtons, I believe, should be my tension. Or I could round it to 2,300 newtons, because I think that is the element, the 2 digits of accuracy. let's double check there and see if I end up with what they say. Yes, the textbook also has 2,300 newtons based on their rounding. Now they went about it a slightly different way. So if you want to check their results, it's on page 131. If the equation version makes more sense to you. I solved it in a slightly different way using less like adding of trig and like moving around of values, but more looking at the diagram and then like logicking out the different components. That's what makes sense in my head. You figure out what makes sense for you. So if you want to take a look on page 131, there is another different way of solving that problem. Cool. Let's continue going and take a look at our next piece, which is a little stop and think. Nice. All right, a Martian lander is approaching the surface. It is slowing its descent by firing its rocket motor. What's the correct free body diagram for the lander? Okay, so for this one, I'm actually going to do a motion diagram and figure it out from there. So I know my motion diagram is that it's coming in hot and then it's slowing down on the way down, right? So I'm going from a lot of velocity to less velocity to less. That means that my overall acceleration is in the upwards direction. So that means that my overall net force has to be in the upwards direction. But I also know that gravity is pulling on the Martian lander. It's the gravity of Mars, not the gravity of the Earth, but there should still be a weight component. So I do need some weight going down, and then I need a bigger arrow going up for the rocket motor, right? The thrust of the rocket motor is pushing it up. And I believe that one leaves me with A. I have a net upwards for my net force. So D gives the accurate net force, right? That's good. B doesn't give the right net force. None of those give the right net force, but I do need to make sure that I also have a downwards force because I know that there's the weight of the Martian lander. So I'm gonna go with A. All right, so that reminds us to talk a little bit about weight. So weight is a force. Weight is equal to the force of gravity. So that is the mass times the acceleration due to gravity, or specifically g, the positive version of the acceleration due to gravity. So here I have weight is equal to m times g. The apparent weight, so sometimes your weight is not the same as your full-on weight. Your apparent weight, weight apparent, is equal to your normal weight plus your mass times whatever acceleration you're under. So one way that you could change your apparent weight is just jump up and down, right? Push up, push down, push up, push down. And if you pay attention, it feels like there's more force or more weight on your feet when you're landing and when you're pushing up and taking off. There's the least force on your feet when you are up in the air because there's no ground pushing on you, right? Once you're up in the air, you're just cruising. You could also feel this if you've been in an elevator. When the elevator accelerates upwards, it's moving a little bit faster, and so it's pushing up more on you, and you get a greater normal force, right? Your weight, your real weight, hasn't changed, but because you have this extra acceleration upwards, you have an upwards net force, and so you have a greater apparent weight, right? Your normal weight plus your mass times the acceleration of the elevator. If the elevator is going down, it would be the opposite, right? I could subtract my weight. I would take my weight minus the mass times the acceleration of the elevator, because the acceleration of the elevator is negative. Okay, so that jumping example brings us to our next idea, which is free fall. In free fall, there is no normal force. I know that there's no normal force because if I'm up in the air, there's no ground pushing on me, right? I need something pushing up on me to provide a normal force. So when I'm up in the air, no force! I was in free fall for a little bit. I was free falling up and then free falling back down. The acceleration was always down. My weight was still there, but there was no ground pushing up on me, so no normal force, right? No feeling of weight. My apparent weight would be 0. Okay, so let's stop and think. You're bouncing up and down on a trampoline. I wasn't, I was just bouncing on the floor, but okay. After you have left the trampoline and are moving upwards, your apparent weight is, okay, so I've left the trampoline, I'm now up in the air. If I'm up in the air, there's no normal force. There's nothing pushing up against me. So I'm gonna say that I have no weight, right? I would be in free fall. So I'm up in the air, nothing's touching me, I'm in free fall until I hit the trampoline again, and then I start feeling weight again. So I'd go from lots of weight to no weight, lots of weight. So my apparent weight is, it is less than my true weight, and it is also 0. And 0 is going to be the more accurate answer, so I'm going to go with 0. Okay. Let's see. Back up to the top, and let's keep going. I'm going to pause there, and we're going to come back for part 2, where we start analyzing forces on an incline. So far we've been on a flat surface. When we come back, the incline. And that way we get to start using more trig. Hooray!